Hi everyone. Today we're going to study irrational numbers. By definition, a number s is called irrational if it cannot be written in the form p over q, where p and q are integers and q not equal to 0. We have examples here: square root of 2, square root of 3, square root of 11, pi, negative of the fraction square root of 2 over square root of 3. Also this decimal 0.10111011101111 and so on. For decimals, we say that decimals that are non-repeating and non-terminating are irrational. We have this theorem. Let p be a prime number. If p divides a square, then p divides a, where a is a positive integer. This theorem will help to prove that irrational numbers are not rational. Now we have proof by contradiction. To prove whether a number is irrational, we use a technique called proof by contradiction. Proof by contradiction is a method to prove the statement P by using the double negation law. This method consists of 3 steps. Step 1, we assume that not P is true. Step 2, find a contradiction. In other words, find that not P is actually false, which means the negation of not P is true. Then step 3, conclude that P is true. That is, P is logically equivalent to negation of not P. Let us see this example. Prove that square root of 2 is irrational. Our step 1, we assume that not P is true. Our proposition P here is square root of 2 is irrational. The not P correspond to square root of 2 is rational. So for step 1, we will assume that this is true. If square root of 2 is rational, we can show that square root of 2 equals a over b. This a over b must be in lowest term. It means there is no common factor between a and b, where a and b are integers and b not equal to 0. Further, both a and b cannot be even integers. Otherwise, the number 2 becomes a common factor for both a and b. Now, step 2, let us find a contradiction based from these statements. That is, let us find that not P is actually false, which means the negation of not P is true. What we're going to do here, let us square this equation. The square root of 2 becomes 2 equals a over b when squared becomes a square over b square. Let us cross multiply this b square to the number 2 on the left side, so that becomes 2b square. Or we can write a square equals 2b square. The constant 2 with a b square gives us idea that the square of a is an even integer. Since a square is even, it follows that a itself is even. Given that a is even, we can now represent a equals 2k, where this k is any integer. Now let us solve for b. Let us substitute this a equals 2k to the equation here. The 2 equals a square over b square. This equation now becomes 2 equals the square of 2k over b square. The square of 2k becomes 4k square. Now let us cross multiply b square with a constant 2 on the left side. So we will have 2b square equals 4k square. Let us divide this equation by 2. So we will get b square equals 2k square. The constant 2 on the right side is telling that the square of b is an even integer. Now it follows that b itself is even. It means we found a contradiction. Our computation here tells us that a is even and b is also even. It contradicts our idea earlier that a over b must be in lowest term. We can go now to step 3. We can conclude that p is true. Our p is here. So we say that, therefore, square root of 2 is irrational. This is our final answer. Example 2. Prove that square root of 3 is irrational. Step 1. We assume not p is true. It means we're going to assume that square root of 3 is rational. If so, square root of 3 equals a over b, where a and b, this b not equal to 0, are integers. Also, we say that this fraction a over b is in lowest term. Now, step 2. Let us find a contradiction. By squaring on both sides and rearranging, we will have this new equation. 3b square equals a square. Let us regard this as equation 1. By this equation, we can see that 3 is a factor of a square. Therefore, a square is divisible by 3. And by theorem, it follows that a is also divisible by 3. So we can write this a equals 3 times c for some integer c. Now let us substitute this value of a to equation 1. So we have this 3b square equals the quantity 3c that is raised to power 2. Simplifying the right side, we have now 9c square. Let us divide this equation by 3. So the value of b square equals 3c square. And this is now our equation 2. From here we can see that 3 is a factor of b square. It means that b square is divisible by 3. And so b is also divisible by 3. Therefore, a and b have at least the number 3 as a common factor. But this contradicts the fact that a over b is in lowest term. This contradiction has risen because of our incorrect assumption that square root of 3 is rational. So we conclude that square root of 3 is irrational. Let's have more theorems. The sum or difference of a rational and an irrational number is irrational. The other is the product and quotient of a non-zero rational and irrational number is irrational. So we have example 3. Prove that 5 minus square root of 3 is irrational. Step 1, we assume that not P is true. It means we're going to assume that 5 minus square root of 3 is rational. If so, this 5 minus square root of 3 equals a over b, where a and this b not equal to 0 are integers. Also, the fraction is in lowest term. In some books, they say that a and b are coprime. Now step 2. Let's find a contradiction. Rearranging this equation, we have now 5 minus a over b equals the square root of 3. Now, for the left side value, we're going to combine as a single fraction, and it becomes 5b minus a over b. Since a and b are integers, the fraction 5b minus a over b, that is the left side value, is rational. Also, the square root of 3 is rational. But this contradicts the fact that square root of 3 is irrational. This contradiction has risen because of our incorrect assumption that 5 minus square root of 3 is rational. So, we conclude that 5 minus square root of 3 is irrational. Example 4. Show that 3 square root of 2 is irrational. Step 1. We assume that not P is true. Therefore, we assume that the 3 square root of 2 is rational. If so, this 3 square root of 2 may be expressed as a over b, where a and b and this b not equal to 0 are integers, and a and b are coprime. Then step 2. Let's find a contradiction. We arrange this equation and it becomes square root of 2 equals a over 3b. Since the number 3 and this a and b are integers, the fraction a over 3b is rational. And so, the square root of 2 is rational. But this contradicts the fact that square root of 2 is irrational. This contradiction has risen because of our incorrect assumption that 3 square root of 2 is rational. So, we conclude that 3 square root of 2 is irrational.